One of the first things that we need to understand when we start looking at quantum mechanics and we look at the atom and try to understand both the structure of the atom and what happens inside the atom is we do need to consider electromagnetic radiation. And to consider electromagnetic radiation, we're first going to look at light. All right, visible light is simply one type of electromagnetic radiation. All right, when I look at fireworks, I have different things going on. We've got the booming sound that we hear and the light that we see. And if we look at the speed of light versus the speed of sound, which one's faster? The speed of light is. This is also why we can sometimes use when we hear thunder versus when we see lightning to gauge how far away a lightning storm is from us, because the difference in the speed of light and the speed of sound. Now we can do a lot of different things with light. One cool thing is we can take prisms like this, and if we shine white light through the prism, what we end up getting is a separation of a rainbow, where the prism is capable of separating the white light up into individual wavelengths where we see rainbow colors. I had these really, well, I still have them, but they're put away. I have these really cool candlesticks that are prisms, and I had them displayed in my dining room at one point in time, except the angle of the light that hit them during a specific part of the day would shine the rainbows on the wall, which would drive the dogs nuts, and they'd start barking like crazy. But prisms are really cool because prisms can separate out individual wavelengths. All right, and then when we look at, the colors that we see, okay, our white light is shining the entire visible spectrum onto things, and then we're either reflecting or refracting various parts of that visible spectrum to see the colors that we see. So here is some electromagnetic radiation, and you can see that we've got high energy, medium energy, and the low energy radiation. And so things that are high energy, highest energy being gamma rays, and then X-rays, ultraviolet radiation. And then this little tiny expanded part here, that's our visible spectrum. So the visible spectrum, what we can see with our naked eye, is actually a really teeny tiny part of the full electromagnetic spectrum. It's not very big. Okay, and so then we've got, our violet down to our red light. So violet light is actually higher energy than red light. Violet light has a shorter wavelength than red light does, and so violet light is higher energy than red light. Okay? And then we get into our lower energy light, our infrared, our microwaves, and our radio waves. Now we can't see with our naked eye anything outside of the visible spectrum. When we start looking at things like ultraviolet radiation, we have specific detectors that let us detect in the ultraviolet region. People that have used low light, like infrared goggles, what they've reported is it's not actually the normal thing that you would see. It's what you're seeing is heat signatures at that point. And so like you see these like kind of shapes, and it takes some training to learn how to interpret what you're seeing in infrared goggles. This is just an interesting, just so you can get a visual perspective of the size of the wavelengths, because some wavelengths are teeny tiny, some are super huge. And so if you think about it, like the size of a radio wave is like the size of a human. Somewhere between microwaves and radio waves is like the size of your fingernail. And so just to give you an idea of kind of what those size comparisons are. All right, when we look at wavelengths, different wavelengths are going to give us different colors. All right, and so again, red light is a lower energy, blue light, violet light is a higher energy, and then the brightness depends upon the amplitude. So the amplitude is how tall a wave is. So like this versus this, that would be different amplitude. All right, and so the larger the amplitude, the brighter the light is. So like here you can see higher amplitude brighter, lower amplitude dimmer. It's not as easy to see the way it translates onto this, but on some computer screens, you can see that the red of the higher amplitude is a little bit brighter. All right. Then when we look here, we've got, our wavelength is our distance per cycle, and you can see where I've got the two hash marks written there. And so when we're looking at this, a long wavelength, all right, is low frequency, and is lower energy. Okay, so low frequency, I don't have very many of them repeat per cycle. Let's see, frequency is cycles per second. And then my short wavelength is a high frequency and higher energy. Okay. All right. And so when we look at our slides, you know, we've got wavelength is the distance between our identical successive points, frequency, the number of peaks that pass a given point in a second. And so wavelength, we use this symbol right here. That's the Greek letter lambda. And then frequency is the Greek letter nu. All right, so wavelength is lambda, frequency is nu. All right, and our frequency is our cycles per second, which is oftentimes given in hertz. And so I have a relationship right here in red. The speed of light is equal to lambda times nu, is equal to the wavelength times the frequency. And so if I know the wavelength, I can figure out the frequency because speed of light is a constant. If I know the frequency, I can figure out the wavelength because speed of light is a constant. Okay. And so when we look at some of these things, all right, when we think about how fast a wave is, so the speed of a wave is the distance traveled per unit time. Okay, and so we get cycles per second, and we have meters per second, and those cancel, or not meters per second, meters per cycle. And so we get meters per second. Okay, and then again, that amplitude is the height of the crest. Okay. All right, so let's just practice a little bit here. All right, I've got a dental hygienist using x-rays. The patient's listening to a radio station, and we're looking out at blue sky. So I've got 3 different things going on with 3 different wavelengths, and I need to know the frequency. This didn't display correctly, but this should have a little thing up there. That's an interesting unit called an angstrom. All right. 1 angstrom is equal to 10 to the negative 10th meters. Angstroms aren't used as often as they used to. When I first started studying chemistry, and I started college back in 1999, all right? So when I first started studying chemistry, angstroms were still used pretty regularly. We defined the size of an atom in angstroms back then. Now you see nanometers more frequently used. Nanometers are a common unit, 10 to the negative 9th meters. And so they're not as unusual as angstroms, but angstroms are still floating around there. All right. And so we want to figure out what the frequency from each of these sources happens to be. All right. So our frequency is going to be equal to the speed of light over lambda. Okay, so let's start with our x-rays. So I have 1 angstrom. I have 10 to the negative 10th meters, and every 1 angstrom is going to give me 1 times 10 to the negative 10th meters. Now, why do I need it in meters? Well, my speed of light is in meters per second. And so in order for my units to cancel out properly, I have to end up using meters. All right, so my wave or my frequency here, I'm going to get my 3 over whatever we need times 10 to the 8th meters per second over that. And so I'm going to get a frequency here of 3 times 10 to the 18th inverse seconds. Okay? All right, my radio waves. All right, so I had the speed of light. Okay, we had 325 centimeters. The easiest way to do this is we're just going to do it this way. We have 325 times 10 to the negative 2 meters. There you go. You don't have to put it in correct scientific notation when you're doing this type of a problem, because that's not your final answer. Your final answer will be in correct scientific notation, but you can just do the conversion from centimeters to meters by tacking on that 10 to the negative 2. All right, we're going to get 9.23 times 10 to the 7th inverse seconds, and then our sky, same speed of light, that's a constant, hasn't changed. Okay, and that was 473 nanometers. We have 10 to the negative 9th meters in every nanometer, so we're going to do the same thing. We're just going to take the 473 times 10 to the negative 9th meters. We don't need to do anything complicated. You just tack that 10 to the negative 9th on there. You're good to go. And we're going to get a frequency here of 6.34 times 10 to the 14th inverse seconds. Okay. All right, I have 2 coming up that I want you to practice. All right, so here we've got sodium vapor lamps. I've given you a wavelength in nanometers. What's the frequency? I'm going to give you the answer. You're going to try the problem on your own. All right, your frequency is going to be 5.09 times 10 to the 14th inverse seconds. When you have a wavelength that's in nanometers, your frequency should have an order of magnitude of 10 to the 14th. Okay? And then the last one I want you to try is this one right here. Okay, so KPBS here in San Diego operates on a 89.5 megahertz frequency. And so this time I want you to try to calculate the wavelength. All right, well, it ends up being pretty similar. The wavelength is going to be the speed of light over the frequency. Okay, and so we've got a conversion there from megahertz, and so what you should get is a wavelength of 3.35 meters. So try those. The math isn't hard. It's just an easy division. The hardest part on these is making sure that you put everything into the correct unit such that the meters can cancel out with the speed of light, and that you know how to enter everything into your calculator properly. So one of the biggest things is that when you're doing these types of division, you know, you should have, you know, parenthesis 3.00 times 10 to the 8th, close parenthesis. You may also type it in as like 3.00 E8, close parenthesis, or on some calculators it's just a single E, 3.00 E8. Okay, but you want to put that in parentheses, and then you do the division of your 89.5 E6, and it's very important to put that in parentheses. If you don't put these in parentheses, what your calculator will do is this. So if you try to type it in like this, what your calculator will do is it will do this part, and then it will multiply the whole thing by 10 to the 6th. So you don't want to do it this way. You want to make sure that you're putting everything in parentheses correctly. Otherwise, your calculator might misinterpret what you mean. So sometimes it really is a matter of figuring out how to be smarter than your calculator. All right, so that is our look at electromagnetic radiation and the beginnings of our understanding of waves.